So I hope you enjoy the keynote. Welcome to the first talk after the keynote. So Gisela Rossi is going to be talking to you today about dictionaries and what is behind the scenes. And she's a software engineer and co-organizer of PyLadies London, which is a really nice meetup that I advise you to check out. I have been going there for like 3 months, and they do a really good job. So please give an applause for Gisela Rossi.
Thank you, Anna. Well, thank you all for being here. It's really nice to see you. As Anna said, my name is Gisela, and today we're going to be talking a little bit about dictionaries and what's so beautiful about them. So this is a quote that was in a book that I was reading. It's the beauty about things changing so much is a lot of that book is already obsolete. But dictionaries are everywhere. It's not only in the code we write as users, but also behind the scenes. So the classes we define have dictionaries behind for the attributes. In namespaces for modules, they are literally omnipresent. And because they are omnipresent, they are constantly changing, constantly evolving. So this talk will have 3 parts. The first part will talk about the main engine behind dictionaries, so namely hashing, and what you can tweak about this if you need to personalize. The second part will talk about some security stuff with dictionaries. It's a topic I'm very interested about. I have been working on security for the last year, and I think you will like it, honestly. I think it has been a quite interesting evolution. The third part will talk about some miscellaneous optimizations dictionaries have had. The selection is completely personal. I think they are very interesting, and there are some quite old from like 9 years ago, and some that have been quite recent, added in the Python 3.6. So let's start with hashing. Let me start from the beginning, just in case someone is not familiar with this. I don't want to lose anyone right now. So what is a hash function? A hash function is a function that can be used to map an arbitrary size data into an integer. And it must satisfy that if 2 objects are equal, then their hashes should be equal. But we will not settle here if we talk about a good hash function, because a good hash function should always be efficient, and it has to minimize collisions. We'll talk more about collisions in a second. So what do we do with hash functions? We build one of the most beloved data structures in the world, the hash tables. Hash tables are amazing, and you probably run into them many times. You maybe even run them into coding interviews, which are an all-time favorite, aren't they? And the beauty of them is that they are very efficient. Most of the things you want to do with them are doable in constant time. And this is why Python dictionaries, and also Python sets, are implemented using hash tables. And here we have an example of something that is quite puzzling when you just start coding. It's talking about, OK, I create my list. I try to add it as a key to a dictionary, and it says type error unhashable type list. And this is because we have this data structure behind as the main engines for dictionaries. And we said we have type error unhashable. OK, fair enough. Give me the definition of what hashable is. And I'm going to read it with you. An object is hashable if it has a hash value which never changes during its lifetime. This is the official definition. And it can be compared to other objects. Hashable objects which compare equal must have the same hash value, as we set as the condition for a hash function. And hashability makes an object usable as a dictionary key or a set member. This is exactly the type error we run into. And now let's digest this definition a little bit more, right? So it says it needs a hash function. So this, under the scenes, needs a dunder hash method. And let's digest it a little bit more. We never change during the lifetime. This means that it cannot depend on mutable attributes. And this will be important if you need to customize this behavior for your own classes. And it can be compared to other objects. And this basically means that it needs a dunderec method. So So are user-defined objects hashable? If I define a class, would this be hashable? Well, by default, yes, and it's the identity. But this is personalized. This is something you can personalize, and this is something you have to proceed with caution. But hopefully, this will serve as kind of a roadmap on the things you don't want to stumble upon, and the things you do want to do. So you can override them. If you override, so you already saw in the definition that you need a dunder egg and a dunder hash. And what happens if you override one and not the other, or what happens if you override both of them? So if you override dunder egg, but you don't override hash, Python automatically says this is unhashable. I'm not going to consider this hashable, and I set dunder hash to none. OK. What happens if you don't want to override egg, but you still want unhashability? Well, you can do this yourself. You can set dunder hash to none, and this is done. OK, fantastic. But I do want hashability, so what do I do? I mean, if I do want, what can I do? Well, you can define these methods yourself, but you have to make sure the attributes that you use for the definition never change. And this is part of the definition we saw when we saw hashable, which is fine. And then here I put an example of how you can do it. So you don't need to become a cryptographer to define dunder hash. You can use the built-in. So basically, imagine I'm defining a class person, and I want to say if two persons have the same name, then I'm going to consider them the same person because I have this weird system. Then basically, I use what is very common to use is just a tuple of those immutable attributes. And I'm done. This is the way I'm going to go about it. So let's talk about security now. And there has been quite an interesting evolution on dictionary security. So the first version of our dictionaries was use a non-cryptographic hash algorithm, kind of a variant of FNB. This was very efficient, but it was exploitable to a deny-of service vulnerability. What does it mean? If an attacker would send you keys designed to collide, then it could trigger the hash table worst case performance, which is quadratic. Nobody wants a quadratic performance in their things that are everywhere. So then we came up, well, not we, I wasn't involved, but as a community, we came up with an evolution for this. We came up with saying, OK, we will keep the core of our algorithm. We will keep FNB, but we will try to add some randomization to it. This was actually configurable with Python hashseed, so you could turn it off by setting Python hashseed to 0, or you could play with it if you know what you're doing. And although this was never abused, it was rightly pointed out that it didn't quite solve the problem at the bottom of it. It was still theoretically possible to abuse this. And it also created some performance issues because this was considerably worse than the first version. So we got to the one we have today. This was introduced in PEP 4.5.6, and basically this PEP introduced a family of options of cryptographic functions that we could use to replace FNB. Basically, the beauty of this is that the analyzer compared and said, OK, zip hash is going to be the one we will be using now. And this will solve the problem at the bottom of it and also improve the performance we had in version 2. So what's the state of the supported Python versions today? If you're using a Python supported version, where are you? There are a couple of .27 that still use original and randomized, so version 1 and 2. But all currently supported Python 3 versions use zip hash. And this is at least something better. And until something better comes out, this is going to be what we will be using. OK, sorry. Let's talk about optimization. So as we said, Python dictionaries are everywhere. And because they are everywhere, they are highly optimized. And this means not only we base them in a structure that is efficient in itself, but we then start to tweak and tweak and tweak until we get to the best we can do. This is an optimization that was proposed by Hettinger, and it's actually a space optimization. We have on the left what was until Python 3.6, I think, how our hash tables would look. You see that there is always a lot of empty space, and if you start inserting elements, at some points it will just resize because it has to guarantee that there is a certain percentage of the space free at all times. But what does this mean? This means that basically you are wasting a lot of space, and you are guaranteeing that you will waste a lot of space all the time. Exactly for every empty row, you have 24 bytes that you're wasting. And now we have the one on the right. So basically, we keep a dense table with all the entries, and then we keep just an array of the indices to see which ones are the ones we have been adding. This only affected data layout. It didn't affect the hashing. It didn't affect the algorithms in place. So it was a very good change. It was significant memory savings because on the right, on the left side, on the old version, as I said, you were wasting exactly 24 bytes per empty row. And on the right hand, on the new version, it depends on the size, but you are saving at least 20 bytes. Iteration became faster. Resizing became faster, and it touched less memory. And now dictionaries remember the order of the items inserted. This is actually a side effect, I think. But I think it's something that is quite nice for dictionaries to have at the moment. This is an old one, key sharing dictionary. And actually, this one is related to the one I'm explaining next as well. So behind the class attributes, there is a dictionary. And if you were here yesterday for the Python object model talk, you saw exactly how to access that dictionary. And that is not so weird to do it. OK, so there was a PEP 412 that basically says, OK, so my dictionaries are going to have these keys that if I instantiate my class several times, they all have the same keys. OK, maybe they can share these keys. I don't need to replicate the name. I mean, the value will be different, but the attribute name will be the same. And this led to a memory reduction of at least 20 to up to 20% in some cases. This was a change from 2012, I think. But it's still today present in the dictionaries we use. And this is actually linked to that one. This one is also quite an oldie. So basically, what it means, how to explain? Sorry. Dictionaries with the string keys are handled differently. So what does it mean? It gets to a point when it needs to compare if two things are the same. If this is any Python object, then the comparison is quite difficult, and it needs to call down the rec, and it needs to do a lot of stuff. But now, what if it's a string? Comparing strings is something much easier, much simpler. So actually, we can introduce this optimization. So if we are talking about just strings, then I'm not going to call down the rec. I'm just going to compare them. And another thing that is good about this is that there is no possibility of raising an exception. So this is something that is also quite linked to the other one, because classes' attributes names are also strings, so it's hand in hand. So that was my talk. I don't know if I spoke too fast. I think I did. It's just 15 minutes, but I tend to do that, sorry. So yeah, thank you. I really hope you enjoyed it. What I wanted for you to take out of this is the will to kind of go and research more. This is a very interesting and constantly ongoing process. I'm also going to leave this. I'm also going to probably tweet the slides because it has all the reference to it. And yeah, I hope you enjoy it. Sorry for speaking so fast. I tend to do that.
Personally, think that the speed was right. I could follow. So unfortunately, we're not going to have questions. However, not right now. However, she's going to stay here all day, and we're going to have the coffee just right after this talk. So you could ask her any questions or talk to her about anything that you might like. So again, thank you, Gisela, for the talk. I really like it.
Thank you. I appreciate it.